Hi guys, Mrs. Cotting here. So today we're going to be talking about molecular geometry, also known as Vsepr theory, VSEPR. So basically this is a theory that uses the Lewis structures that we learned about earlier this week and allows us to predict what shape molecules are going to take. Okay, so before we get started, we do need to do just a very quick refresher on Lewis structures. This is going to be pretty important for today's lesson. So I'm going to do a couple of examples, and I think my example got cut off. It's underneath my periodic table where that bullet is, but that's okay. I already know what it's supposed to be. So let's go ahead and try this out. Let's do NH3 to begin with. So pretty straightforward example. Okay, so basically the first thing we have to do is add up the total number of valence electrons that both of these elements have. So for nitrogen, nitrogen is here on the periodic table where I underlined it. If you count over 1, 2, 3, 4, 5, you can see that nitrogen has 5 valence electrons. Hydrogen is in the first column, so it only has 1, but there are 3 of them, so 3 times 1. This gives you a total of 8 electrons. All right, now to figure out what element goes in the middle, well, there are a couple rules. The first rule is that hydrogen can never go in the middle. It's way too little. It only has a 1s orbital, so it can only hold 2 electrons. Being in the middle just isn't possible. The other rule is that the closer something is to fluorine, or the more electronegative it is, the less likely it is to be in the middle. So we only have one option here because hydrogen can't go in the middle. It has to be nitrogen. So I will put my electrons like that. The first thing you want to do now is connect the electrons with bonding electrons. Remember, each bond consists of 2 electrons. I have 8 total. So this will be 2, 4, 6. The last 2 are going to go on nitrogen because hydrogen only can have 2 electrons. The only thing you're ever going to have for hydrogen is 1 bond. So this is what the Lewis structure looks like for NH3, just like that. All right, let's do another one. This one we're going to do CO2, carbon dioxide. All right, so the first thing we have to do is add up the total number of electrons. Carbon is in this column, so it has 4 valence electrons. Oxygen is here, so it has 6. There are 2 of them, so 2 times 6. 2 times 6 is 12. 12 plus 4 is 16. So we're going to have 16 valence electrons. Now, to figure out what goes in the middle, you're always going to put the most electronegative element on the outside. So because oxygen is more electronegative than carbon, oxygen will go on the outside. Just like that. Connect them first. 2, 4. So I've used up 4 of my electrons out of my 16. So the remaining electrons I'm going to go ahead and put around the outside first. This one I am going to put some on the oxygens because oxygen is not hydrogen. It wants to have 8 electrons. So I'm going to fill up the octet of oxygen first. So we already used 4. So here's 6, 8, 10, 12, 14, 16. So I'm all out of electrons. The problem with the way that this Lewis structure is drawn right now is that if you look at carbon, carbon only has 4 electrons around it, which is not stable. Carbon, just like every other element outside of hydrogen, wants to have 8 electrons. So because of that, I need to move electrons into the bonds. So first thing I'll do is move these 2 electrons into the bond. And when I do that, it creates a double bond. I'll do the same thing on the other side. And when you do that, let me erase the ones that I moved. You get a structure that looks sort of like this. Now, if you want to, you can move these 2 electrons on the top so it's more symmetrical, but you really don't need to do that. It's not important. The important thing is just like how many bonds and how many lone pairs are on each atom. So this would be the Lewis structure for carbon dioxide. You can see carbon has 2, 4, 6, 8 electrons around it. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And then this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Remember, each bond counts as 2 electrons when you're counting the number of electrons. So everything around my carbon dioxide molecule has 8 electrons. Okay, so those are Lewis structures. Lewis structures are actually very useful in Vsepr theory. So basically, Lewis structures, when you draw a Lewis structure, it only gives you a 2-dimensional picture of what the molecule looks like. It's flat. They don't really tell you anything about the 3-dimensional geometry by themselves. When I say 3-dimensional geometry, I'm talking about the overall 3-dimensional shape of the molecule. Obviously, because we live in a 3-dimensional world, molecules are going to take up 3-dimensional shapes. Vsepr theory, Vsepr, it stands for valence shell electron pair repulsion. Theory can use Lewis structures to tell us how a molecule looks in 3D. So whenever you're trying to figure out the 3-dimensional shape, the first thing you will always do is draw a Lewis structure for the molecule, because that's the first step. Vsepr theory predicts the direction in space of all the bonds around an atom. Here are a couple of examples of 3-dimensional shapes. The top one you can see has sort of a bent shape, whereas the bottom one has a sort of, it looks almost like a tripod shape. So Vsepr theory allows you to predict where the bonds are going to be around the molecule. So how does Vsepr theory work? Vsepr theory is based off the fact that electrons are negative. So remember, electrons have a negative charge. So when you have bonds and lone pairs around an atom, those electrons will repel each other. It's not likely that you're going to have 2 bonds very close together because they're going to repel. So when you're figuring out the shape, the electrons are going to orient themselves so that they are as far apart as possible around the central atom. And then also, lone pairs of electrons take up more space around a central atom than bonding pairs of electrons. Because bonding pairs of electrons are shared between 2 atoms, it's possible to move those a little bit closer together than it is a lone pair. A lone pair is only on that individual atom. It's not being shared, so those electrons spend all their time around that atom. It needs more room because of that. Okay, so here are some examples. So here's a simple one. This is carbon dioxide. We just drew that a minute ago. If you have 2 bonds on the central atom, the electrons from each bond are going to repel each other. So when you're trying to figure out what this is going to look like, you're going to get a picture that looks sort of like this. This type of molecule is called a linear molecule. And basically, the reason that carbon dioxide takes this shape is because this allows those 2 bonds to be as far apart as possible from one another. Now, this here is called a ball and stick model. It does not really show a lot of the detail on the Lewis structure, so it doesn't show the fact that these are double bonds. It doesn't show the lone pairs on the oxygens. The entire purpose of a model like this is just to show kind of what the shape is going to be. So for carbon dioxide, it looks a lot like this. This angle, this is called a bond angle. A bond angle just tells you the angle between 2 bonds in a molecule. In a linear molecule where one bond is on one side and the other bond is on the opposite side, the bond angle is going to be 180 degrees because that's what this angle is right here. So that's what this means. So what would happen if there were 3 bonds on the central atom? What shape would that take? Well, it looks sort of like this. This is called a trigonal planar molecule. So if this is your central atom and your central atom has 3 bonds, those three bonds are going to kind of put themselves in a triangle shape because this is as far apart as they can get from one another. So the bond angle for this is 120 degrees. So that would be the bond angle of something that's trigonal like this. Now, if there are four bonds, it's actually a very common misconception for if there are four bonds to kind of draw them like this. But what you have to be careful of is that if you were to draw it like this, that would be a 90-degree bond angle if it was square like that. The actual shape that four bonds will take, it kind of looks like a tripod like this. Remember, molecules are 3D, so they do not have to be stuck in a plane like this. This here has a bond angle of 90 degrees, but this one here has a bond angle of 109.5. So this shape here, it's kind of difficult to tell what it looks like. Basically, it looks sort of like a tripod that you would put a camera on. So you have one going up, a couple that are going down and kind of away from you, and then one that's coming towards you. So this is a three-dimensional shape. The angle between all of the bonds is 109.5 degrees. So by taking this shape instead of this shape, those electrons are able to get a little bit farther apart. This shape is called a tetrahedron. So maybe you've heard of that shape before. It's a very, very symmetrical shape. Here's what it looks like if something has 5 bonds. So if you have your central atom, and your central atom has a total of 5 bonds, you're only ever going to see molecules like this for things that can hold more than 8 electrons around them. In order to have a molecule like this, your central atom needs to be in the 3rd period or lower. The reason it needs to be in the 3rd period or lower is because then it's able to expand its octet with its 3D orbitals, and it can hold more than 8 electrons around it. So if you had 5 and each bond contained 2 electrons, that's 2, 4, 6, 8, 10 around that central atom. So this is only possible for 3rd period or lower. Now let's talk about this shape a little bit. This shape is called a trigonal bipyramid. If you kind of look at the shape, you can see there are 3 that are in the middle that are sort of in a triangle shape. This one's going away from you, this one's coming towards you. So all 3 of these are actually 120 degrees apart, just like trigonal planar. But then there's also one on top and one on bottom. The bond angle between these two is 90 degrees. From these two is 90 degrees. This one is also a 90-degree angle, and this one is a 90-degree angle. It's called a trigonal bipyramid because if you were to connect all of the atoms together, you can see it sort of makes a pyramid shape, but it's like 2 pyramids stuck together. So it's called that because there's 2 pyramids. Trigonal bipyramid, bi means 2, so that's why it's called that. So that's 5 bonds. Now if you have 6 bonds, again, this is only possible for for central atoms that are in the 3rd period or lower. This is called an octahedron, which you may have heard of before. So the thing about octahedrons is that these have all 90-degree angles. So every single bond angle on this is 90 degrees. So if you were to look at this bond angle, that's 90. This bond angle is 90. This bond angle is 90. This bond angle is 90. It's an extremely symmetrical shape. And again, it's only possible if the central atom is in the 3rd period or lower. Okay, so those are the main shapes. Now, what do you do if it's not a bond, but it's a lone pair on one side of the molecule? Well, the lone pair still kind of takes up the space that the bond would have taken if it was a bond instead. So this is kind of similar to the example that I showed earlier in the slides. However, lone pairs do take up slightly more space. So when that happens, this is no longer going to be a 120-degree angle. It actually shrinks down to 119. So because the lone pair takes up so much space, it actually pushes the bonds closer together just by a little bit. It's not a huge difference. It really usually only goes down by like a degree or two, but it is noticeable. All right, so here is a chart of all the Vsepr geometries. So here's how you use it. So basically, what you do when you are using a chart like this, the first thing you always want to do is draw the Lewis structure. Then what you're going to do is look at the central atom, just the one in the middle of the molecule. You don't really care about the ones on the outside of the molecule for this. You're only looking at the central atom. You're going to count bonds and lone pairs. That total, so say you have like 2 bonds in 1 lone pair, that would be a total of 3 pairs. That tells you which row you're going to look at. So if you have like just 2 bonds and that's it, you're going to look at this row. If you had 2 bonds and 2 lone pairs, that's a total of 4, you would look at this row. If you had 4 bonds and 2 lone pairs, you would look at this row because that's a total of 6. So you just kind of look at the total of bonds and lone pairs you have. Now to figure out exactly what shape you have inside that row, you look at the top. So if it's all bonds and you don't have any lone pairs, you're going to look at the first column. If you have 1 lone pair, you're going to look at the second column, 2 lone pairs, the third column, and so on. So you just kind of use this table as a chart to tell you what the molecule is going to look like. So let me go ahead and show you with an example. So we're going to do an example together. So we're going to try water. Water is a very easy one to draw. What is water's predicted shape, and also what about its bond angles? So the very first thing we have to do is draw a Lewis structure for water, H2O. So take out your periodic table and count the valence electrons first. Hydrogen only has 1. Oxygen has 6. So this gives us a total of 8 electrons. When you're drawing the atoms in the molecule, oxygen has to go in the middle. Hydrogen can't. So you draw it like that. We have 8 electrons. So it'll be 2 here, 2 here. So that's a total of 4 so far. The last 4 electrons have to go on the oxygen because hydrogen cannot have lone pairs. So that would be the Lewis structure for water. So that's the first step, is to draw the Lewis structure. Once you have that drawn, you're going to look at the central atom, so just the oxygen. My oxygen has 2 bonds, as 1 on each side, and then it also has 2 lone pairs. So that's a total of 4. 2 plus 2. Okay, so that tells me what row to look at in my chart. So if I go back to my chart, 4 is here. So I'm going to look at this row. It's going to be one of these 3 shapes. To figure out which one it is, if you go back to the water, I have 2 lone pairs. So 2 lone pairs is this column. So this is the shape that it would take. This shape is called bent or angular. I've never heard angular before. I've always heard bent, so that's usually what it's called. And the bond angle is, it says less than 109 degrees. So 109 is kind of like what it would be ideally if you didn't have any lone pairs, but because we have two lone pairs, those lone pairs will squish the two bonds together a slight amount. So I think water's bond angle is like closer to 107 or something like that. But let's go ahead and draw it. So, well, I guess look at this picture kind of carefully first before we go. This is what we're going to be attempting to draw for water. The oxygen is in the middle, hydrogen is on either side. So that's kind of how we're going to try to draw it. So we have oxygen in the middle, hydrogen on either side. It's bent like this. If you were to draw your bond angle in, here it is. It's less than 109 degrees. So I'll draw that. For this type of question, if it's asking about a bond angle, you don't need to know the exact number. Really, the only important thing is that you know that it's less than 109 degrees. Okay, and then our two lone pairs will go on the top, sort of like that. So this would be the molecular shape of water. Okay, so there's your example. We're going to be practicing with this a little bit more tomorrow. Tomorrow's the last actual day of class, which is kind of sad. This unit usually goes on a little bit longer. This is probably we're going to end it for this school year. So go ahead and try the practice. Send me an email if you need any help. All right. Bye, guys.